Okay. It's my honor to have Xinlei here for the first talk. So Xinlei was also a LTI alumni, so he was here from 2012 and 2018. And after graduation from here, he moved to FAIR, Physical AI Research, now Foundational AI Research, and has been done a bunch of work actually in the core part of the representative learning for computer vision, with like local versions, MAE, and so a fun fact that Xinlei and I were actually office mates back then in the day. And even he was not at office, I can sometimes monitor his work because he was remote to his laptop. And the way I can see the mouse moving, etc.
Oh yeah, I remember that too. I forgot to turn the display off.
Yeah, so I can actually see like what Shin is coding and doing back then. Okay, so the stage yours.
Mm-hmm. Okay, thanks Chen Yan for the fun introduction. A bit more about myself, just in case Chen Yan didn't show up, and I prepared some slides. As Chen said, I got my PhD from this department, actually, and I was here about 5-6 years back. And back then, I was mainly working on visual knowledge learning. And then I went on and started my full-time job at Facebook AI Research, FAIR. And my time there, it's almost a PhD time already now. So my time there is divided into two parts as well. So one is the first 2 years, I spent some time to do multimodal learning with both language and vision. And then I moved my interest to self-supervised representation learning without language. So it's about 3 years or more than 3 years now. So when I was invited to this talk, I was super excited, but then I had to face this dilemma here that I have to either talk about my multimodal work related to language from more than 3 years back, or I will talk about new things that's less related to language, or maybe it's even anti-language. So I made a decision. I decided to talk in a retrospective way about my language and vision work. And the primary reason for that is that I think meta-level thoughts about research, it lasts longer than 3 years. And they are worth sharing with you guys. And I think this is probably the most important thing to share. And it's my first time to share with it. And specifically, I'm going to talk about visual question answering. So this is a popular task back then that requires models to jointly understand language and the images to perform the task. And I'll talk about my two journeys to the VQA challenges hosted back then in 2018 and 2020. Luckily, we won both times, but it was with two very different research philosophies. So this is something I would like to share. For those of you who do not know what is visual question answering or VQA, the task setup is very simple. So V stands for vision, it's images. Q stands for questions, so it's questions expressed in natural language. And A is the answer. So here, the question is asking about what number is taking the shot, and the system is expected to output the number. And there was a challenge that's considered a standard benchmark for multimodal vision language understanding. It's called the VQA challenge. It was hosted for 5 years, or maybe 6 years back then, and for 2 of them, we participated. So first, I'll talk about my first journey that happened in 2018. We went to the VQA challenges right after my graduation at CMU, and it's in fact the first challenge that I have ever participated in my life. And what to do about it? And at that moment, we decided to go with this additive philosophy, which is actually a very common mindset for participating in any challenges. And I'm trying to make an analogy here that this is more like a hot pot of Chinese cuisine, that we have some base or some framework, and then we just put everything to it, and we get the output. So to put it in a more abstract form is to start from some standard or state-of-the-art pipeline. So I'll say P here, and then we will keep adding ingredients to it. We can do multiple trials and errors for A, B, C, all the way to Z, and we will aim for the absolute performance. So that's the only goal of winning the challenge. So for VQA, back then, a very standard pipeline is something like this. So given a question and image pair, we will first feed them separately to compute some representations. So for images, we get visual representations. For text, we get textual representations. And then we have some multimodal fusion model module in the end that outputs the answer. And at that moment, in 2017, the best performing model, which won the challenge last year, was something like this. So they call it bottom-up attention model to highlight the visual representation they have discovered in the work. So here, for visual representations, they have something called bottom-up attention, which I'll explain later. And then for text and multimodal fusion, they do something quite simple, and it's less related to what I'll talk about. So starting from this framework, we did something called a Pythia that won the challenge in 2018. And the journey toward winning the challenge is actually very simple. So as I said, we just add more and more ingredients for the win. So we started with bottom-up attention. We added some architecture changes. We did some learning rate warm-up, blah, blah, all the things. And then we did this standard practice of doing model ensembling and get our final number. So I'll just list some of the examples we have tried. So in detail. So one is this learning rate warm-up trick that we wanted to train the model with a higher learning rate, but because the higher learning rate usually offers better performance according to our experience, but with the higher learning rate, it also incurs the risk a gradient explosion, so we cannot train the model anymore. So back then there was this trick we borrowed from computer vision practice, that we just do a learning rate warm-up starting from a small value and then linearly increase it to a higher value. And in that way, we can train the model with a higher learning rate and achieve better performance. So it helps about 0.9%. And then another example is data augmentation. So it's another known thing that we can use more data to train our model. So specifically, we used visual genome and visual dialogue. They have similar orders of numbers, images, and question pairs to train our model. So that helps about 0.6%. And a third example, and the last example, is that we did some diverse model ensembling. So instead of ensemble the same best model with multiple trainings, so you can see from the blue curve here, we actually try to combine the output of a diverse set of models. So models trained with different training sets and or visual features. And we find that the practice of diverse model ensembling helps a lot. And it's the most effective trick that we had in this challenge. And not only that, we participated another challenge called VizWiz in that year with the same set of code bases we have developed, Pythia. And for VizWiz, a very particular thing is that they are more close to the real world setting. So for the VQA, they basically just ask Amazon Mechanical Turkers, given an image, come up with some question and answer pairs. And those people are mostly visible people. But for the VizWiz challenge, which I believe is partially collected here at CMU, they would ask blind people, and the blind people will ask real questions that helps them unblock challenges in their life. So you can see the questions here is mostly about what is this, what color is this. It's more close to the real world setting. So we thought this challenge is meaningful, and we participated in that as well. And again, we followed this philosophy of trying to add things. So starting from Pythia, which was the framework we developed for the normal VQA challenge, we added several things like syntax features, or VQA pre-training, and again, doing some model ensembling. And that helps us to win the challenge. So one particular thing I want to briefly mention is the syntax features. So it does seem like for blind people, they would want to learn about the products they're interacting with in their daily life. And a very important aspect to understand the product is to read some syntax from the image. So yeah, here is an example. The blind person is asking, what does this bottle say? And the model has to read the text in the scene in order to answer the question well. So what we did was we just run some OCR some modules that can read text from the scene and add that to our model. It helps a little bit. I do think there's more room it can help, but it helps. So what are the takeaways from this particular journey to the VQA challenges? I mean, this is some of the post-challenge thinking I had. Is it something that, for example, bottom-up attention, it really works? Well, we already learned it from the last year's winner, right? It was using bottom-up attention. It was their proposal. How about architecture changes? Well, if we try hard enough, we are almost guaranteed that architecture changes can help. How about learning rate warm-ups? Well, it should, because we already know it works well for other vision applications, and maybe in NLP as well. And for all the other findings we have, it's kind of not so satisfying. Although we have won those challenges, we don't have something on our own that's newly discovered, that's not already known to the community. So I believe the only value there is to show that adding all these things up in a hot pot, it can show the state-of-the-art result, but it does not offer a very good scientific message to the community. The value of it is quite limited. So with that, I would talk about my second journey to the VQA challenge, and as veterans to that challenge, in that particular journey, we are trying something different. So this particular paradigm we are following is kind of ablation as the main theme. I'm not sure who of you guys know what does ablation mean. Yes. Well, I use this a lot when I was writing papers, following the previous papers as examples. But it turns out ablation means to actually remove ingredients. And in fact, this is a term coined by CMU folks, Alan Newell. According to the Wikipedia, I just checked last night. It's just some new saying I would like to share. And fundamentally, why do we want to do ablation? So why we want to remove the ingredients? I think one of the biggest reasons is this Occam's razor, that if things are equal, then we would prefer the simpler solutions. And this is closer to a person with a machine learning background heart, that simpler systems usually generalize better. So we followed this as our main research philosophy to approach this problem. So this time we are trying to do it with a more scientific mindset. So again, we are starting from some standard state-of-the-art pipeline, but instead of adding ingredients, let's try removing ingredients and see if they are as crucial as they claim to be. So back then, because we are participating in 2020, the challenge winner from last year, 2019, was again this this framework with some other components shuffled. So it still uses bottom-up attention, but for other components like language representation, textual representation, it uses LSTM with some attention. And then with multimodal fusions, they have some even more fancy things that do not matter to us. But what we see that's invariant is that for all the challenges of 2017 to 2018, the visual representation is always this bottom-up attention. So we are curious to see what is the magic there and whether it is something so important as it claims to be. So having identified our candidate of ablation, we took a deeper look at what bottom-up attention is. And the idea is very simple at a high level. It is to represent images with regions. It will use multiple spatially localized features to represent an image. So it's multiple, it's not a single vector. It's spatially localized, so you can see that each bounding box here will produce a feature to represent that bounding box or that region. And this is different from a traditional model's output in that the bounding box are located around the objects. So instead of uniformly located on a grid, it will be located around some objects that it thinks is important. And they call it bottom-up attention because these bounding boxes or these regions are selected only from image pixels. So it's computed only from image pixels without any top-down prior or top-down guidance from the text. And this is a high level. And in terms of a low-level implementations, here is how they implemented it. The details may not matter that much, but what they do is they train a standard object detector called FastRCN on a data set, the visual genome, and then they use some standard ResNet as a backbone. And given an image, they have two additional steps once they have computed the features from the ResNet. So they will do region selection. So this is to score all the regions and then select it from the pool of candidates. And then it will, for each of the candidates, it will compute some features. So I'll call it region feature computation. So what it does is just average pool the features from each region and gets the output. And this idea has dominated the leaderboard since its proposal in 2017 until 2020. And if we take a closer look at this bottom-up attention, I mean, this idea seems to be very attractive. It intuitively should do better over grid features because, for example, as they claim, that they can localize individual objects better. Maybe they can capture both the coerced global structure and the fine-grained details in the image because they can zoom in and zoom out with regions. And maybe they can allow the model to model the object interactions explicitly. But is it actually the case? because there are a lot of other confounding factors we find with that pipeline. For example, one is this pre-training task. Because in order for the model to propose these regions, it should pre-train on some task related to object detection, which is to get bounding boxes from image. And the previous practice is always to pre-train it on some image classification task. And then the pre-training data set is also different. For classification, we pre-train on a data set like ImageNet, but for detection, they train it on visual genome. So we find it's a very interesting study to do in order to understand better what the role other confounding factors played. So that's the work we did back in 2019 to actually do the controlled study for these bottom-up features. As the title suggests, we find that grid features are actually performing as well, or maybe can even perform better than region features. But I think it's worth sharing our approach of how to study it. So in order to study it well, we have to first fix some variables. So to study the impact of some other variables, we have to fix the current ones. So we'll fix the pre-training task and the data set, and that was visual genome object detection plus some attribute classification. We will fix the backbone, so that's the same ResNet architecture we tried. We also fix the input size. That seems to be very important because high resolution images usually result in better results. And then we fix the evaluation task and metric. So that's VQA and the VQA score. And then we fix the VQA model. So we used our own Pythia model, which won the challenge the year before. So we performed several studies. The first study is to just get grid features from the same layer. So on the left side, I'm showing this quite complex pipeline that does object detection, that involves region proposal, region pooling to get n regions and their representations. On the right is our simplified version, but getting features from the same layer. So what we did was we just wired the same number of the same set of parameters and get the features out. But instead of computing region level features, we get the features for the entire image. So it results in an H by W grid. And we find that regions, so if we keep all the settings the same, pre-training task and the data set, the result is already very, very close. This is compared to the same format of features, so compared to the grid features, pre-trained on the classification task on ImageNet, we find it's much closer to the region features we get by pre-training on visual genome with the object detection task. So it's 0.7% between the top two, but then it's almost a 3% improvement from ImageNet classification. And with that promising signal, we, as a next step, we tried to improve the pre-training for grids. This is because fast RCN as a detector R actually stands for regions. So it is a particular detector that operates on regions. And that means it's very likely, it's highly likely, that a lot of the designs made for that detector is highly optimized or maybe overfitted to that region level tasks. So we find we can just make a very small modification to this pipeline. So instead of doing 14 by 14 region level pooling, we do it one by one. So this basically breaks the spatial representation of regions in RCN. And again, we do the pre-training and we extract the grid level features with the same practice. We find that this improved pre-training can already catch up with the performance of the region features. So the top two numbers are the same from the last table, but in the bottom, instead of doing 14 by 14 regional interest pooling, we do 1 by 1. It of course degenerates the object detection performance, but that's a pre-training task. We don't care about the pre-training task. And for the task of VQA score, I mean, this is a task we care, we find the trend is opposite. So for regions, the feature quality is made a little bit worse. But for grid features, it's improved and it's actually slightly better than the best region features we get. So with this, we find that with the pre-training task and the pre-training data set fixed, we can indeed get grid features to work just as well as region features for VQA. And just to make the analysis more solid, we also studied something like the number of visual features. And the motivation for that is N regions are sparsely sampled for the region level features. But for grid level features, we find, it's densely sampled. It's densely sampled on everywhere. So that means N is usually smaller than H times W. And this can be a practice that can benefit grid features because grid feature naturally has more information. Well, it has a larger model from the input side. So that's what we did in the next study. So we tried in the horizontal axis to also increase the number of regions from left to right, so that it can match the number of grid features. This is shown in the red dot here, and we find that no matter how we increase the number of region features, it's already saturating, and the result we get is quite solid in that sense. So even with the larger regions, it's still the same. So then we did some attention visualizations to show that region features are making reasonable attention maps, but with grid features we can also do. So here, when the question is about is it a summer thing, the region features will look at the snow, and for grid features it will also look at a sparse set of locations, but it's also on snow. And we have shown more attention visualizations in our paper, and this is a good practice that we not only show successful cases but also show failure cases. So for example, the bottom one, both region features and grid features are not doing so great. So you ask how many boats are there. It did attend to the boats regions, but for counting, the model does not seem to work well for both region features and grid features. And we started to generalize once we have this finding to make this claim more solid. So we tried different backbones. Remember, the backbone was fixed from before, so we tried a larger backbone. We tried different VQA models. So not only the winner from the year before, we also tried MCAN. So that's the state-of-the-art multimodal fusion model. We also tried different VQA tasks, so not just the VQA and also with from before. We also tried different other tasks. Also, it's vision and language. It's about image captioning. And we find for all these settings, grids are roughly similar to regions. Sometimes regions are better, sometimes grids are better, but it's roughly similar. So then we ask the question, why our grid features are working, why previous grid features were not working. Of course, as I mentioned before, the pre-training task, it matters a lot. We have already shown that if we train visual grid features from ImageNet classification, it's not working as well as pre-training object detection with the visual genome. And another important factor we want to highlight is about input image size. So that's why we wanted to fix the input image size in the beginning. That we, for classification, the standard practice is to do 224 by 224 during pre-training, and then extract the features with 448 by 448. But the detection default was 600 by 1000 for image input. And we find that it plays a very important role, both for ImageNet training and VG training. And in fact, if we further increase our default feature size from 600 to 800, it can further improve the performance. So besides the conclusion, I mean, hopefully I have convinced you that region features, grid features are roughly the same, and we don't really need those complex pipeline for region features. What are we gaining from this? So I think there are two things. The first one is this simplification that machine learning people really want, that if all things are equal, we want the simpler pipeline. And for region pipeline, because it has to deal with regions, it has two extra steps, region selection and region feature computation for fulfilling this task. And for grid features, we don't need that. Just needs a single forward pass through our backbone. And because of that, one very practical practice is that we can do end-to-end optimization. So before, I mean, at around that time, visual question answering tasks are always computed on frozen visual features. So they will dump the visual features, they will pre-compute and then dump those features on the disk and then train a VQA model on those frozen features. But with grid features, we find that it can be easily optimized end to end. And indeed, this is a practice we are doing right now for multimodal understanding, that in order to get good performance, we always do end-to-end optimization. This is the first one. And a practical second benefit is the speed up, because we can skip all these steps. In fact, these steps are taking most of the time for compute. So you can see region selection is taking about more than a half, and region features also taking more than a third. And with a ResNet 50 backbone, we can get 40 times speed up compared to the region features. So this is great, but in the end, I want to briefly mention about one caveat that I mentioned when I talk about the attention map, that region features are great features. They both seem not so great for counting questions. So we specifically investigated into that, and we find that grid features can also work well for counting if we do modulated convolutions. So at that moment, people also come up with additive modules for regions. And the idea was to follow the reasoning path of human beings, how they count objects. So what they do is that with these region features, they will get each of them and then do some kind of symbolic counter that's first to count this object as one, and then the second and the third, based on the relationship between or among the regions. This is great for understanding. This is great for knowing what this model can do. But on the other hand, it also has a downside that for every task, this time is counting, every task you will have to design a new model to deal with that task. So right on the right side, I'm showing a question about spatial reasoning. So for that, one may need another design to accomplish that task. And then this is not so scalable. If we have 1,000 tasks, then we'll need 1,000 models. So what we propose with the grid features is that it's very general. We just do modulated convolutions. I'll skip all the details. But we find that this can be applied for all kinds of reasoning tasks. So it can work with counting, it can work with the spatial reasoning, can also work with other things because it's a more general module that you can plug in and get good performance out. So we did a lot of analysis to this module, but one particular analysis I just want to highlight is to see the contribution of plugging movie into a normal VQA model and see how much it contributes for different types of questions. The text here is very small, so I'll do a zoom in version. So you can see that for counting type of questions, like how many people, how many the movie module helps the most. So it's indeed the case that our movie module is helping for counting, and it's validating our claim. So with movie and with this investigation into regions with grids, we participated in the challenge in 2020, and luckily we won there. We won the challenge there as well, and this is a good demonstration that VQA models can work just fine by removing the key component regions, from the pipeline. But then the story does not end there. We actually find that the next year's winner in 2021, they also tried both regions and the grid features. We are glad that they used our grid features as part of their winning solution to win the challenge. But we are sad that people are just being very addictive to the additive research when trying to participate in challenges. So what they did was they combined both the region features and the grid features, among other things. I think they tried all of them and win this challenge. And nowadays, I think the state-of-the-art model for VQA is actually in the hands of grid features. So you can just train a gigantic vision and language multimodal understanding model, and that has no component of regions there, and it's almost 86, 87% last time I checked. Okay, so here, to sum up, I have talked about two journeys to the VQA challenge. One is additive, so we start from something and we just add more ingredients to it. The other is more ablative, that we start with something and we try to remove some key components for it and still show that it can work. And indeed, they both worked and helped us win challenges. But I want to make some more comments about these two philosophies of research. So for additive research, I think this is great for pushing numbers. And that's what I did when I was a graduate school. And I'm pretty good at that, and pretty good at using 100% of the cluster, and nobody else can use it. But there are downsides of it. For example, it's easier to overfit. The target is too clear. You are trying everything you can to a particular benchmark. So there's a big risk that it can overfit. And because we add more and more components to it, I think it's very hard to analyze which one contributes to which. So it can create some problems for other people to understand, but at the same time, it can also create opportunities for people who try to analyze it and show something different. And for ablative research, I think it's better for scientific understanding, and it's better for finding fundamental things. So if you cut the system to simpler, so it cannot be made more simple, then you may find something that's very fundamental, and you can generalize from there. And sometimes it can be more efficient because it removes some complicated things. But the downside for that is that it's harder. Sometimes it's harder to make it work. You are fighting an upward battle. Yeah, so this is about my talk. My email is on the upper right corner, and feel free to reach out to me if you have more thoughts about this additive and ablative research. And happy to discuss more about it. Yes?
I noticed that there were no error bars or significance, standard deviations in the results here. Is that common in vision? And do you think that having some more statistical rigor would help avoid having spurious additions to these fancy models?
Yes. Yes and yes. So indeed, it's a common practice in computer vision. For all the numbers we have here, we definitely do this standard deviation check, especially when we try to reproduce each other's results. So we run it multiple times to make sure that the pipeline is okay. Yeah, but I love to see more this error bars in our work, in more research work. And on the other hand, it's actually a magic that deep learning is reproducible. Like the first time you train the gigantic network, it reaches a certain number, for example, ImageNet, 76% for ResNet. But I mean, isn't it magic that for the second time, you start from some random initialized other parameters and still can converge to some the same level of performance? It's something to think about.
Yeah. So you mentioned that additive research is sort of great for pushing numbers, but maybe has some disadvantages here. Do you think that the system of having a VQA challenge every year, where the team that gets the highest numbers sort of gets some sort of accolade here, is pushing the field or incentivizing additive research? And how do you feel about that? Do you think that we should keep doing that?
I mean, organizing a challenge like VQA is great, but I think in practice, a lot of people will try to push the number as a single objective. And I mean, there's a saying that when a metric becomes an objective, it stops being a metric. But I see things change. So for example, in a lot of challenges these days, people will not just get awarded for become the best, the winner. They will get awarded for having the most creative solution. And that's a little bit more subjective, but I think it's healthy for the community.
Yeah. And then a follow-up, what do you think the role or goal of challenges in the community is?
I haven't organized a challenge myself before, so I haven't thought too much about it. Yeah, but it's good to have them around and to benchmark the progress we have. But on the other hand, I think maybe it's very hard to evaluate things like ChatGPT on a benchmark.
From the perspective of conceptual contribution, would you still consider using regional features to be an additive research? Because wouldn't the success of regional feature itself be saying that the contribution of object detection to VQA would be that it will give this backbone features that better represent the background objects that exist in the image, and that is what's contributed to its performance on VQA. And using grid feature will be saying it's okay. It's saying it's fine that we use all of the features because they will still encode that background objects feature. But then using the fact that the model is encoding the background objects feature itself is still a contribution to scientific understanding. Because if we use grid level, like you said before, if we use grid level features, we have we have a height times width number of features. And if we use regional features, we'll have like n number of features, and n is usually much smaller than h times w. And but they will still get similar levels of performance, even though like with regional features you have much fewer number of features. And then even later on, you can say that if you increase the number of regional features to the same level as grid level features, they will eventually converge to the same.
Yeah, so I mean, I can make one remark on that, and it's less about VQA. It's more about object detection. So for a while, object detection has this two types of approaches. One type is actually based on grid features. So there's no region proposal methods, and it was not so performant for a while compared to a multi-stage method that's based on regions. You will first propose regions and do things. And people would think that two-stage methods are slower than one-stage method because it has more stage. But it's not the case, right? Because if you spend more compute in the second stage and spend only on those focused regions, it is better than spend the same amount of compute everywhere in the first stage. So it's like a selective computation mechanism. And the most important example is probably mask Gaussian. So mask Gaussian, if you do the mask computation on all the locations of an image, it will incur a lot of compute. But if you spend the mask computation only on a few sets, then it saves a lot of compute and it's faster. So this is also my experience from some other work I didn't mention here. Yeah, but over the past 6 years, I've been involved in a lot of works.
So would one claim be that like the difference is not in what features you extract, but the amount of compute?
In some sense, yes. I mean, if we can find some method that can leverage the power of compute, I think that's holding the future in hand. Yes.
I'm curious if there's been work to kind of scope out where things like grid features versus region features work, right? Like in the scope of this challenge, there might be different subdomains, or there might be different data sets you could look at entirely to say like, oh, this is where region features work, versus this is where grid features work. Is there work like that or plans for it?
Well, I have to say, the work we have done, we stopped doing that because I shifted all my attention to self-supervised representation learning in the past 3 years. But I think there is some follow-up work that try to understand this better. I cannot think of it out of my head about specific examples, but there should be.
Fernando, this one, and then I go.
Yeah, I'm wondering about comparing these two approaches from a strictly engineering perspective, right? So if I'm running a big organization, additive research seems much easier to sort of like, I have 50 teams who each work on an individual component independently, and then I'll sort of like throw it in the hot pot. Versus ablative research is much more of an engineering lift, right? Because I need to sort of take something that's worked and pull it out, and there's tons of dependencies all over the place. Not that it's not important, because like you're clearly like it can lead to these step changes. But I wonder if you can comment on this.
Yeah, I think it's more of a short-term versus long-term thing. I think within the short term, maybe it's great for the org to dispute the forces and try different ideas to the existing system. But then I think in the long term, it's great to do two things. One thing is to find something fundamental, and that cannot do without ablative research. And then the other thing is to always come back and then revisit some of the things you have already added. And that's also part of ablation, because maybe if the new feature you add will cause the previous feature to be obsolete. Yeah, I mean, as a research part of the company, we definitely focus more on the long term.
I'm going to steal you for one, and then I'll go to the back of the one. I think part of what I don't fully understand in terms of the intuition with the grid features is basically the role of receptive field. So I think this is kind of related to this discussion we're having, which is that if I just increase the number of regions for my region proposal network, I'm still going to get a distribution which is not uniform over the space. And if I have my grid features, but I have very large receptive fields, then those are potentially, object-sized regions, and maybe even capturing some notional spatial relation. And then in the self-supervised work that you've done more recently, because we're in transformer land, we have basically global attention, and so everybody can talk with everybody. So I think there's this other dimension to this that I don't have a strong intuition for, which is like, is it the fact that the grid is better if we have either its large receptive fields or its global attention, or it's some mechanism that allows for long distance information sharing. And if I don't have that, then having a prior that tells me objectness is sort of useful. Is there a tension there?
Yeah, I guess my intuition tells me yes. I think empirically, the networks we have studied here, the receptive fields are out of the borders of images for sure, and they're enough to capture the interactions between different locations, among different locations. On the other hand, I think locality, like being able to look more about nearest neighbors and become more focused on that, is actually a very important prior of all our architectures. You mentioned transformers, but for vision, our transformers are operating on patches. And each patch is forming a local neighborhood. And if you remove that local neighborhood, say if you just do a random fixed shuffling of locations and chop them into 16 by 16, like 256 pseudo patches, and do transformers on top of it, it does not work. We have tried that.
One last, go ahead, maybe two last.
Yeah, thanks for the last presentation. A high-level question about your philosophy of research. You talk about additive and ablative. They are most about manipulating with the existing stuff. But if you're anything on your comments on how to go with coming up with something new components. Anything from your research experience you can talk with researchers?
Yes, I can comment on that. Looking back, for self-supervised learning, there are two important works I usually talk about in my talks. One is having this ablative flavor. So it's simple Siamese network. It's actually removing components for for state-of-the-art existing frameworks, and in that way can actually connect all of them together. I mean, I didn't get chance to talk about it, but it's a type of research philosophy we follow. But the other work, masked autoencoding, I think it's actually different from additive or ablative research that I talk about today. Because I think both additive and ablative research are doing local search. They are starting from some existing frameworks and they add or subtract things, remove things. But for masked autoencoding, I mean, we are trying to create something new. Well, it was something new for computer vision, but I think BERT was already out there way before. So I mean, one way we can do new things is to get ideas from other fields. I mean, you can view that as additive research or whatever, but I think this is my answer right now.
One last, I think, in the back corner. Yeah.
So I want to know if you could give a summarization of for what vision tasks that bridging features you clearly useful or like better than grid features. So also I want to know like if in type of reasoning tasks if bridging features will be more useful because it can be used to track objects.
I can think of two scenarios. One scenario is where I mean, you have to play with regions. Regions are part of the output of the system. For example, if you want to edit the image by removing some regions, and then you need the bounding box over there. I think a second scenario, I think it's related to the comment from this two-stage versus one-stage thing, is that when we want some fast prototyping, then maybe getting the top 100 features from regions, region proposals that captures the gist of the image, that's great. I mean, I think at that point, at one point, it was 36 features for each image. So it's much faster than grid features that has to deal with the height times width. Yeah, so I can think of that scenario that if you want to do some fast prototyping and limited budget, then of course it's good to go with that and pre-compute the features.
Cool. All right. Well, thank you again for humoring all of these probing questions and philosophy. So thank you.
Okay, thanks.